Alright, in calculus, we're looking at the process of finding the area between two curves. This particular exercise is really sort of getting you to look at the graphical approach and how to use technology, but the core of this is a trig identities thing. So just for the record, on our next test, we're not going to be dealing with trig identities, but if anyone is interested in how to do this work without a calculator, because they know they're going to be taking a calculus course down the line in the future, that's what this video is for. But even if you don't want to use the paper and pencil method, I'll explain to you how to use the calculator to do this, just really briefly. First thing it says is identify each curve. So we have C1 and C2. One of them is y equals cosine squared, and the other one is y equals the cosine of 2x. And I can tell right away that C1 is going to be cosine squared because C1 is a curve that has no negative numbers. And when you square things, you always get positive numbers. So this one has to be the cosine squared, and then the bottom one has to be the cosine of 2x. The other thing I need to know is where is the intersection. Now I could use the intersect mode of my calculator, or I could use common sense. The cosine of 2x, for example, has a period of pi radians, so it's going to be at pi. Or I could look at the fact that x is 3, and this is just to the right of 3, so it has to be pi. There's a number of ways that you can get the fact that this intersects at 0 and pi. When it says determine the coordinates of A, B, C, D, and E, then we could very quickly just write in point A is the point 0, 1. The point B, we could find by intersection is going to be pi over 4. It said coordinates, so I write 0, pi over 4. Point C is here, which is that's B over there. C is going to be the point 0, pi over 2. Point D is the point 0, 3 pi over 4. And finally, point D is already labeled as the point pi 1. Or point E. Okay, and then how I got 3 pi over 4, basically I know that if they go from 0 to pi, this is half pi, this is a quarter pi, so we're going to go 1/4 pi, 2/4 pi, 3/4 pi. So that's how I know that's 0, 3 pi over 4. And then finally 4/4 pi, or just 1 whole pi. Anyway, that's all for parts A and B, and then it says show that the area of the shaded region is pi over 2 square units. So what I did was I took cosine squared of x, and this is how I write it in the calculator. You just write the cosine of x, and then close the parentheses, and then square it. That's how the calculator interprets cosine squared, and then cosine of 2x, and finally I put y1 minus y2, because y1 is the upper curve, and y2 is the lower curve. That produced this particular graph, which is the difference between the two functions. As you can see, this graph looks different than the given graph because we've transformed the function to be an area against the x-axis, which is easier to work with. Anyway, I go to the calculate option in my calculator, and I choose option 7, which is the integral of the function, and left bound I put 0, enter, and right bound I put pi, enter, and it produces the number 1.5707963. I go to my calculator and put pi over 2, and it gives me the exact same number. Therefore, we can say without any question, the integral from 0 to pi of cosine squared minus cosine of 2x dx is in fact pi over 2. The rest of this is for those, again, who were curious about how would they do this if they didn't have a calculator. This is based on something that we should have learned in a pre-calculus class or a geo-trig class or whatever. Whether we learn it or not, you should at least have had some recollection that there's these things called double angle identities. Cosine of 2x, if I look this up on the internet and say double angle identity cosine, this is one of the 3 choices we'll have. Cosine of 2x is equal to 2 cosine squared of x subtract 1. Again, there's a bunch of highfalutin reasons for this, but this is a fact to be proven in a bunch of different ways. For now, we'll take a faith argument. Anyway, the cosine squared is something that I have a trouble integrating, but the cosine of 2x is easier to integrate. So if I could get cosine squareds to look more like cosines of 2x, then I'm in good shape. So here's a cosine of 2x, which is equal to some variation of a cosine squared. I'm going to add 1 to both sides, and then I'm going to divide both sides by 2, And that tells me that the cosine squared can be calculated by taking half the cosine of 2x, adding 1. So instead of integrating the integral that I wrote down originally, I'm going to, everywhere I see x squared, every time I see cosine squared of x, I'm going to replace it with all the stuff in red there, as you can see. I'm going to distribute the 1/2 and collect like terms. Here, 1/2 cosine of 2x minus 1 cosine of 2x is going to be negative 1/2 cosine of 2x. So the 1/2 here stays down, and then half cosine 2x minus 1 cosine 2x is negative 1/2 cosine of 2x. This is something I could easily integrate. The antiderivative of 1/2 is 1/2 x, and the antiderivative of 1/2 cosine of 2x is 1/4 sine of 2x. Don't forget, I'm reversing the chain rule, so this 2 is dividing down, and that's why a half became a quarter. Do this from 0 to pi, and evaluate. When x is pi, we get half pi over 2. The sine of 2 pi is 0. You can find that in your calculator or using common sense. And 1/4 of 0 is still 0. Here, when I put in 0 for x, I'm going to get 0 for the first term, and the sine of 0 is also 0. So I end up with pi over 2, just as I knew I would. So that's the non-calculator approach to that particular exercise. Hope you found this helpful. Have a great day.